Myself and my two colleagues, Dave and Manasa, are going to talk you through a few different aspects of Google's network and why we think it makes for a high-performance network. My section is going to be taking you through the basics, the underlying physical and operating aspects of Google's network that sort of powers Google Cloud. I'm going to talk a little bit how we plan to build our network for resilience, how we operate it in a resilient fashion, and also how we extend this thinking beyond the boundaries of our own network to the internet in general. So let's start off. It's possibly no surprise that Google owns and operates and has built probably one of the largest networks in the world. This network is primarily based on fiber that we've lit ourselves, or we've even built ourselves or in conjunction with partners. Now, what this means is that we can offer a predictable and resilient performance level all across the world. So if we look at the map, you can see here, these are all the network paths that we've built over the 20 or so years that Google's been running. Highlighted as well here, we have some of our major submarine cable investments dating back to 2010 with Unity, all the way through to the more recently announced cables that are coming on stream in the coming year. So this is the network that enables us to serve billions of search query answers. This is the network that enables us to serve billions of hours of YouTube videos to users all over the world. And this is also the network that Google uses to replicate content and services between our custom-built data centers and our footprint, again, across the world. And critically, it's the network that powers Google Cloud. Now, in recent years, what's interesting and exciting for us in the cloud team is that it's our cloud customers and some of their demands that have started to shape the nature of our network investments and network planning. As we go to new locations with new mini clusters and new cloud regions, and as we have to think carefully about how we connect in ways that prioritize maybe latency over resilience. Let me give you an example of that. This is last year, and you'll see here that when we built some new paths between Singapore, our Southeast Asia region, and Sydney, we almost cut our latency in half. It's actually not possible to get that much shorter latency now between these two locations. Okay, and this is a great example of where we've said latency is important, resilience is important, let's build more capacity that makes sense for our cloud users. And we're doubling down in this region. Later this year, we will have two new cable investments, the Indigo cable and the JGA cable coming on stream to add even more capacity and more performance. What's also interesting to think about is that Google is now at a scale in its operations that it can go about planning and building submarine cables by itself. What this means is that we can provide a level of path certainty. We can lay the cable where we need it to go to connect our locations that make sense for Google and for cloud. And we can do it an awful lot faster than traditional approaches where you're working with many consortia partners. So these things are called private cables in the industry parlance. If you want to read a little bit more about some private cables that we've announced, I encourage you to use your favorite search engine and look up the Curie cable, which is going from Chile up the west coast into North America, or the Dunant cable, which there was a press release about some exciting technology Dave will talk about just last week. But the Dunant cable goes between France and America as well. And these are private cable systems Google's building by itself. And we're able to do that because of our scale. Now, the great news for all of you here as Google Cloud customers is that you're able to connect to this network at 134 locations all around the world. That could be directly or through an extensive network of cloud interconnect partners. It has never been easier to get on board our global network. Now, it's great having a huge network, but as our traffic grows and we build new cloud regions and we have to build new paths for new capacity, it's also critical that we maintain and improve the performance of the network. Now, when we're planning, we use extensive simulation whenever we introduce or consider introducing new network capacity. We want to make sure that it is not going to impact our SLOs negatively, or it's not going to do so in unexpected ways. And as part of this, we've actually evolved our planning processes. So we used to use trended historical data on outages and expected failure rates. And we'd run some Monte Carlo type simulations to actually understand what the potential SLO we'd expect to see was. Now we've moved beyond that a little bit, and we're performing more discrete event analysis these days. So what we do is we classify a whole batch of different failure types across the entire network path, and we assign each of them probability curves and frequency curves of happening, blast radius, independency variables. We then push these all together and run them for a fictional, 10, 20, 30, 50 years into the future against a whole different range of network topologies. And what this does is gives us a reasonably high degree of certainty that the network we choose and the additional capacity and locations and paths that we add into it is going to meet and maintain and increase the resilience and the predictability that we care so much about. This sounds like a lot of bother. Is it really worth it? The answer is really clearly yes. Okay, here's an example from 2018, last year. We're looking here at 2 data centers in our APAC region. We have a number of paths. I've obfuscated the data here slightly for commercial reasons on the cables. But you can see we had 2 cuts, 2 dual case failure scenarios where we lost paths on 2 systems at once. And in fact, one of these was what we call a dual case worst failure, where we lost one of the very large paths. These are also quite long enduring events, and that's because in the submarine world, the actual identification of a failure through to the rectification can take months. You have to permit, there's weather issues, the ship may not be available to go and do the repair, it may not find the cable, it may have to remake the repair. Now fortunately, because of all of that planning and effort into building a resilient network that I talked about earlier, no Google Cloud customer and no Google service was negatively impacted by these dual case failure events. Okay, things just went on. And that's what we try and aim for. We try very much to not leave anything to chance when we're building out this network. So now that we've built it in a resilient manner, it's critical that we operate it resiliently as well. And there's 3 aspects to that I want to share with you today. The first is SDN everywhere. It's no secret that we've operated an SDN network on our core inter-data center campus network. However, a couple of years ago, we announced with Espresso that we were pushing SDN right out to the edge, and that process is effectively finished as of now. What does this mean? Well, it enables us to maintain a level of performance and availability right out to the edge of the network that's simply not possible using regular routing approaches and routing protocols. We can optimize our link utilization at the same time as we maintain certain business rules, quality of service aspects, and priorities. It also offers a lot faster convergence than traditional protocols like MPLS running RSVP. Secondly, at the edge of our network, we connect with nearly all significant network operators. And this allows us to hand off directly and reliably close to the end user about 99% of our traffic. So together, these first 2 points translate to higher availability, better performance through Google's Cloud's network than is available through the internet at large. But the icing on the cake is always our SRE teams, so our site reliability engineering teams. If you've not visited the SRE lounge yet, it's across in the back corner. Look for the inflatable unicorn. Google literally wrote the book on SRE, and it's available in the bookshop in the swag corner. We have a number of network SRE teams stationed throughout the world, and it's their role to continually respond and adapt to network events to improve systems and processes so that the reliability and performance of the network continues to improve over time. It's a classic post-mortem culture. Something goes wrong, we don't blame people, we identify root cause, we learn, and we implement approaches and workarounds to build a resilience and a performance that only goes one way, up. Our SRE teams are also on hand to give a second level of support to our customer-facing staff and help on some deep cloud issues that may require a little bit more involvement on the actual network layer. So together we operate for resilience across these three levels. But our network, your traffic, our traffic, doesn't stop at the edge of our network, okay? The internet is a critical part of how all of us deliver traffic to end users, to our customers, and it will continue to be so. So our commitment to performance and to reliability and trustworthiness goes beyond the edge of our network to the internet at large. Now, as many of you know, the reality is the internet is not a controlled space. Bad stuff happens. Issues like route hijacks are a fact of life, okay? Unfortunately, a keyboard error by a small ISP in Africa can really cause global problems, right? As maybe some of you remember from news articles last year, they hit Google. So that's not great. So here's an example. We've got a bad actor. They're doing a couple of things that's not ideal. Let's assume it's not malicious, it's just a keyboard mistake. Anyone could make it. They're going to advertise some Google IP space towards their peers. They're also advertising some IP space from another network out towards the internet. Well, today, these routes are going to start to propagate, and traffic could go the wrong way. Okay, user traffic could end up being black holed, being isolated, just bad things. So this is not great, and we've seen this happen too many times. What's Google trying to do about this? Okay, well, firstly, we're continually enhancing our own monitoring and filtering capabilities. We want to make sure we can get quicker and better at identifying these sorts of issues and responding to them. However, this is a community-wide issue, and so we are working with other organizations in partnership. We've joined MANNERS. For those of you not heard of it, it's the best acronym in the world. MANNERS, the Mutually Agreed Norms for Routing Security. It is an ISOC-sponsored group, and it's really working to try and enhance the security of routing on the internet. So Google has recently joined, and I can announce that shortly we will start applying routing filters based on the routing registry, IRR, to all of our public peering sessions. So we want to slowly encourage other network operators to up their game in maintaining the accuracy and veracity of those IRR records. Now that's great, but it's going to take a little bit of time. Anything on the internet takes time. Hopefully this will be faster than IPv6 everywhere. So the other thing we're doing is something called peer lock. And so peer lock we think will give us some short-term immediate gain. And we're going to work with about 15 or 20 of our largest peering partners to effectively agree an additional level of filtering safety, which will validate not just the addresses, but also the paths that we wish to receive those addresses from. So together, with these two aspects, we believe that a lot of these negative situations will be blocked. It's going to bring additional valuable protection and stability, not just to Google traffic, but because we're such a large part of the internet, to the internet as a whole. And of course, because this is the network that drives and powers your traffic to customers, it'll help Google Cloud customers as well. And overall, deliver a better internet for a cloud. That's enough about our underlying network. I'm going to hand over to my colleague, Dave.
Thank you very much, Donald. My name is Dave Phillips. I'm a colleague of Donald's. So here to talk to you about the performance we have on the Google network. I'll do that by talking about 3 layers of performance, right? We'll talk about the overall network software and the algorithms that you use to talk to us, and we use to talk between our own services. We'll talk about the physical layer and how that applies directly to you and gives you benefit. And we'll talk about the Andromeda cloud layer, so where all of your cloud services live. And the main message I want you to take away is that really at every layer of the network, every level of performance, there's engineering teams within Google working to optimize, get a little bit of advantage, make things faster, make things more resilient. And big investment all the way through it. So in the last 3 years, We spent $30 billion on infrastructure. That's 30 and billion with a B. Sundar announced this year we're spending 13 billion, so 13 and again billion with a B. So let's start to look at some of these layers and the innovation we have at them. Okay, so maybe starting off, let's just give you a snapshot of the timeline of some of the innovations we've had. And I guess some of the things you'll maybe notice is that some of the things on the timeline show up a few years after we've had them live for a while. So there's stuff that's on the timeline that you can't see, that you'll see a few years from now. Somebody will have this presentation and there'll be stuff there, but that's just how it goes. But a lot of the stuff that's public right now, well, Donald talked about SDN. That's a real core of what we do. SDN is the central software controlled way of doing things. Think about your modern way of navigating with maps when it's got real-time traffic versus how you used to use a sat-nav 15 years ago and it was a fixed map, and if everybody went the same direction, it was actually slower, right? So that's SDN with central software control. Our first iteration of this was B4. This is our massive backbone between all of our data centers. We then introduced our Jupiter, which is our massive switching fabric that goes within our data centers, makes all these tens, hundreds of thousands of machines act together as one great big system. Andromeda, the network software-defined virtualization layer that you guys use for building up your cloud. And Expresso, which Donald mentioned, the fourth pillar, which is taking that software-defined capability all the way out to the edge. Other things here, Maglev, our software-defined load, our load balancer. That's been in place at Google now for maybe more than 10 years, taking in all of our front-end traffic. And why all of these base building block infrastructures are very important is we solved these problems at Google to scale to the level we needed to be able to deliver traffic for Google. But these are the same building blocks that are in use for the cloud products. You get to use these same building blocks. I guess I should hold this instead of putting it down, right? Okay, so we said we'd talk about these three layers. Let's talk about performance at the network software layer. So, as Donald mentioned, we want to make the internet better as a whole, right? So not just ourselves internally, but overall. Because if we make it better for everybody and everybody adopts these standards, everything gets faster. So let me tell you about two technologies here. I'll talk about BBR and I'll talk about Quick. So let's talk about BBR first. Okay, so this is an algorithm within, or a manner of implementing congestion control within TCP. So TCP for the longest time was loss-based. From the late 1980s, pretty much been loss-based. Now, that's worked for a long time, but when you talk about modern networks, which typically have high-capacity links but relatively small buffers, actually this is not such a great way of doing it. When TCP algorithms detect loss, they can back off quite sharply. And actually, counterintuitively, on very high-capacity networks, sometimes you don't get such great performance on that. So we need to rethink that from the ground up. BBR is a way of doing that. BBR stands for bottleneck bandwidth, and round-trip propagation time. It's a fundamentally different way of looking at congestion control, and what it does is detects actual congestion and models throughput end-to-end to be able to optimize rather than being loss-based, right? Gives us a very, very significant advantage. There's a sort of a nice little graphic here, because it's able to detect the actual congestion rather than reacting very aggressively to loss. You get much greater throughput. When we enable this on YouTube, overall globally, we got 4% greater transmit rate, 14% in some countries. These are actually big numbers because that was really highly optimized to begin with. Okay, now very easy for you to use that. As soon as you talk from your front ends to your back ends in Google Cloud, you're already using this. As soon as you go through anything which terminates, on the Google side, your sessions from then on are automatically using BBR, right? So you get that. So when you're doing big transitions transactions rather, back to Google Storage or anything like that, you're using this Beebee or you're taking advantage of it, you're getting that throughput. Let's change tracks. Let's talk about another innovation. Let's talk about Quick. Quick is quick UDP internet connections. And what this is doing is a way of optimizing your setup. So where you would have used HTTPS and TLS over TCP, okay? Now when you do that traditionally with using HTTPS, using TCP and TLS over TCP, over TCP, you're typically taking about 3 round trips to get that initial setup, 3 handshakes for that to happen. With Quick, if you've already talked with the server, you can begin transmitting traffic immediately, right? So very quick, especially for that first page load. When we enable that, we're seeing about 8% faster page load. Again, these were highly optimized things to begin with, so that's actually a big number. How you enable that yourselves is on your load balancer inside the system, you just enable Quick. Very easy to do. Quick is also very, very good and was designed from the ground up to multiplex for multiplex streams. So traditionally with TCP, if you have some multiplex streams, you lose some traffic, all streams are held up. With Quick, it's just the actual stream that's lost the traffic. The other streams are good. So also very good for moving between wireless and mobile networks, as you may be doing here, because you have a connection ID rather than a tuple. Okay? So again, these are ways we're optimizing things at the fundamental software algorithm layer to make things faster. Let's talk about that second thing I mentioned, which is let's talk about improvements at the physical layer and how they manifest to you. Well, so this graphic here, you may have seen some press about last week. This is our Jewelcase transatlantic cable that we just announced. Donald mentioned this. So this is our second private cable. We actually have 13 subsea cable investments. So what that means for you, firstly, is that we're going to have that deterministic capacity available for you when you need it, but a lot of innovation at this layer. So this cable here is going from Virginia to France. And normally when you're in a data center and you see like a fiber tray or a duct or a trench, you see hundreds of cables or thousands of fibers, right? Subsea, it's very, very different. The amount of power you need to regenerate those signals means in a typical subsea cable, you have at most maybe 6 or 8 fiber pairs within that. This cable here, Jewelcase cable, this uses something called space division multiplexing. It's the first cable undersea to do that. It means we can reuse some of the same repeaters for multiple fiber pairs instead of just one. So this system here, this actually has 12 cables, world first, right? It's a lot of innovation at that level, right at the physical layer. We name all of our cables after famous scientists. So Curie, Jewelcase, who's the first Nobel Prize winner. The next one will be E, so think of a scientist beginning with E. You can guess what that will be. Maybe we can have a competition. I don't actually genuinely know what the cable will be called. A and B were alphas and betas. Okay, so linking back to that. So why does all this matter? Why does having all this physical infrastructure matter and give you benefit, give you tangible benefit? Well, a good way of showing this is our premium tier. So Donald had a really, really good statistic, which is that 99% of our traffic is being handed off directly. So really meaning that it's going really all the way across the internet or across the span between source and destination on the Google network, on this very, very fast, very high performance Google network. Now, our standard tier, this is kind of the way most cloud stuff works, most cloud provider works. If you're a routing person, I'm from Ireland, so I say a routing person, but I've had to learn to say routing person. So if you're a routing person, this is the difference between cold potato and hot potato routing. Cold potato routing is you take the traffic all the way on your own network. That's our premium tier. Hot potato is you hand it off as soon as possible. Okay? This makes a really big difference. If you have premium tier enabled, you're getting a ride on the earliest ingress point on the Google network, and Donald showed you the scale and all of those locations, you're coming all the way across the Google network to your compute, then all the way back across the Google network and then off. If you're doing the standard tier, you're pretty much coming in closest to your compute, and then you're being handed off back to the internet, and you're taking your chances with the wider internet after that. Now, what does this mean in terms of performance? Well, it's a big deal. Don't take my word for it. I actually work for Google. I'm going to tell you it's great. But look at the actual external folks that test this stuff. This is Sodexis. This is actually, I pulled this data just from last month. The graph doesn't actually start at 0. It starts at 3. So you're talking about 1.9x greater throughput going directly across that network, as opposed to going across and taking your chances with the wider internet. And that's kind of what you would expect. If we build this really, really high performance network with all these fibers and all this cable and all this reach, you're going to get much better performance. So that's the premium tier. Now, very easy for you to enable that. Simply inside your console on your VPCs, you're just going to enable premium tier. You don't need to go messing with all this fancy routing. And that's a big message here, that we're able to make all of this technology very, very easy for you to access. It's very complex at our end to make it all work. I actually worked in networking for the last 10 years before I came over to product, right? But in terms of how it works for you guys as customers, it's very, very easy for you to access this and turn it on. So let me just put 3 of those products together as an example. Let's talk about that premium networking. Let's talk about VPC. And let's talk about global load balancing. Okay, VPC is your virtual private cloud. I'll talk about that a little bit later, but essentially this is your main network construct that you build. One of the first things that you build. Here's something to know, is that is inherently a global construct, right? You might use it on a regional basis initially, but that's inherently a global construct. Then let's talk about global load balancing. When you enable this global load balancing at Google, what we do is we give your service a virtual IP address. But then, instead of having to play around with DNS or doing anything like that, we do this much better way, which is we do anycast. So from all of our edge PUPs and our extensive edge infrastructure, we will anycast out that address, meaning that that same address is advertised in all these different regions, meaning that you will be pulled in at the most proximate location on our global network, right? So here's an example. We have Maya in California, and she is pulled in directly to the US West, which is on the West Coast. We have Bob in London going to the same address, which you mapped to your primary DNSA record, and he's been sucked into the London site, so for very fast local performance. And then you have Shen in Singapore, again using the same IP address, DNS, going into the Singapore PUP there. That's what global load balancing does. Now, because that VPC is also global, it's able to do this very clever stuff, like know if certain aspects of your system are overloaded, it can automatically redirect to others and overflow, right? So very, very clever, and very, very easy for you to use the power of this enormous network, turning it on like that. Let's take this diagram here, and let's imagine we rewind it a bit, okay? So I don't have an animation or anything, but let's just pretend we're not at a stage where we have US, Europe, and Asia. Let's just say we've just set up, just to begin with, we've just set up with a few VMs on the West Coast, okay? So what I can do, turn that on, do this global load balancing, set up my VPC, and what's happening there is, well, just all of the traffic is being sucked into the West Coast, right? Then what I decide is I'm really growing here, and I could really use a presence in Europe, or the East Coast, or wherever. So I set up in Europe. Now, because the VPC is global, because global load balancing is global, just by setting up in Europe, automatically all that European traffic, or all the traffic proximate to that region is being pulled in there. And then similarly with that growth in Asia. So very easy to make use of this without very advanced knowledge of the underlying infrastructure. All right. The other pillar I wanted to talk about is performance at the Andromeda layer. So this is the network virtualization layer that all of this stuff works within. Okay, so this is this layer on top of our infrastructure that's going to give you that performance and functional isolation where your infrastructure lives. Okay, let's first talk about this idea of a VPC, or a virtual private cloud. This is the basic building block of your infrastructure. So this is what you define. And what you could think about this, something similar to a network you set up in your data center. This is your own little private slice of the cloud. Now the good thing about this is, firstly, as I said, it's not region locked, it's global. Now, if you have a situation where you're in financial services or medical and you need your stuff contained within a region, yes, absolutely, we can do that as well. But the concept itself is inherently not something you need to define in each region. Replicating that config, you can define it once. You also don't need a VPC for every project. You can do this idea of a shared VPC where you've got a services VPC and then you got host projects off of that. So very easy way to maintain one common security model, one common administrative model. All of your traffic within that VPC is very, very secure. It's not touching the public network, the public internet. And as Donald said, you have all those 134 plus points at which you can interconnect. Okay? So common overall model using this VPC as the base networking block. Oh, wrong button. So this is what it does. This is what Andromeda does. It essentially takes all of our huge infrastructure, all those data centers, all those fibers, all those POPs, and chops it up so that you have your own slice of it. It provides that security, and that functional and performance isolation. So here we can see we've got the green customer, the yellow customer, and the red customer. They're all using 10 space addresses, but that doesn't matter because they're all completely isolated and all working independently within this Andromeda layer using our infrastructure. Okay, so how does it work? Well, in terms of what we do is we push a lot of the networking all the way to the host. In fact, we do that in user space. We push it all the way down to the user space. Why do we do that? Well, firstly, it's very secure. The data plane is not running en route. Secondly, it's a very low footprint, so we can really test it, fuzz it. A very small surface for any kind of security vulnerabilities. Very high performance on a single processor. We're getting 3 billion packets per second. For co-processors, then we'll do more advanced packet rewriting and things like that. But our fast path through a single processor gives us this very, very high performance without needing to rely on any ASICs or any specific hardware. Allows us to iterate very quickly. Allows us to do hitless upgrades. Allows us to do live migrations. Allows us to continually innovate and push features. This is the overall architecture itself. The control plane itself is built as a hierarchy. You have a cluster, cloud cluster manager. You then have a fabric management layer. You then have the open flow layer, which we push the configuration down to at an SDN level. So fully replicated, fully sharded across zones, across regions. And by using that SDN and by pushing the configuration down into the fabric, that allows us to really do this horizontal scaling. And that's a very, let's think about it like this. Think about our internal load balancer, right? Now we have all these different load balancers. We talked about the global load balancer earlier. I'm now talking about an internal load balancer within your slice of the data center. Actually, how you normally implement that is you have a dedicated box or a dedicated machine that does that, or a dedicated VM that does that. We don't. It's all existing within the switch fabric. So it means there's no middle box, there's no choke point. It's configuration pushed out into the SDN layer, which gives you that load balancing capability. So it gives you this near infinite scaling. This is an idea of some of the level of performance we've gotten with Andromeda over the years. So one of the main things we tried to look at is the cycles per byte in terms of transmitting traffic. And as we've gone through the various iterations there, we've had very, very significant levels of improvement, up to 16x and up to 50 byte per cycle improvement. The biggest jump was to Andromeda 2.0 when we put most everything into the guest layer, bypassing the host. Andromeda 2.1, we got rid of the last thread, and Andromeda 2.2, we added a memory copying. And we continue to innovate very aggressively. Just since we talked to you last at the last Cloud Next, let's see, we've introduced LPM, longest prefix matching caches per machine, so for internet-heavy workloads, that makes a big difference. Our Hermes system for network configuration pushes is now twice as fast, about 15 seconds to push the network config versus 30 seconds a year ago. We've dealt with, 2018 there was a lot of very, very large CPU issues, Spectre, line meld, etc. We were able to deal with those very, very easily in the background from you. A lot of scaling in our load balancers, particularly using something called hoverboards. So we're able to scale those load balancers quite a lot further than we were. And look, one thing that all these improvements are leading to, higher performance devices for you, higher performance services. So at Next here, we'll be announcing the 32 gigabit per second VMs. Limit before this was 16 gig per second. Going all the way up to 32 now. In your Skylake machine, that's in all regions. With 16 vCPUs, you can get all the way up to 32, and that network is going to give you that performance. Up to 100 gigs on our GPU level machines too, going into alpha. So if you have one of these high-end GPU machines, you want 100 gig, for that, talk to your account rep. Okay. Now let's look at how we manage and monitor all of those solutions. I'll hand you over to my colleague, Manasa.
My name is Manasa. Okay, here we go. My name is Manasa, and I'm going to talk to you about how we monitor our network. You heard from Donald earlier about how we build our global network for resilience, and you heard from Dave about our investments and innovations to be able to drive for better performance. And I'll talk to you about how we monitor our internal infrastructure to begin with, where Google kind of has a way of monitoring our network at various levels, right? Starting from intrazone, interzone, inter-VM to the edge and so on. But we'll also talk through how we think about monitoring how our end users experience the services that get deployed on Google Cloud. And then we'll also go through how we use all these metrics that get generated to be able to optimize our service delivery paths to our end customers and plan for the future as well. So with that, let's get started. Every machine on the Google network is actually a part of our overarching monitoring infrastructure. We collect near real-time logs on each of these hosts that we have. So it includes metrics like RTT and throughput, and this does not require any additional software to get installed on any of the hosts, so it comes at no additional performance impact to you. What this enables us to do is it enables us to monitor and get visibility into our infrastructure at various levels. We can get metrics at the VPC network as a whole, or for a specific subnet, or drill down all the way to a specific VM instance or a virtual interface. Apart from this collection infrastructure, we've also deployed probes extensively across our network. And this provides us with additional visibility into things like packet loss, latency, and various other metrics. So Google's overall built a network where the network and the host actually play well together to be able to optimize for performance. We built this centralized bandwidth allocation algorithm that's able to actually enforce policy at the host level. And all of this works at the scale of Google WAN. For those of you who are interested in learning more about that, check out the publication that we have called Bandwidth Enforcer, and you should be able to get to know more about that. Okay, moving forward, like I mentioned, let's talk a little bit more about how we think about understanding how our end users experience services that get deployed on Google Cloud. Because from an end user point of view, they don't really care where the network issues are, right? It might be at the Google end or at external to our network, but they just want things to work. So we at Google need to kind of think about it more proactively to understand where the issue lies and work with our partners proactively to be able to manage those issues. So we've built an infrastructure and technology where we're able to understand connectivity issues from end users coming into Google's network itself and be able to attribute that specifically to where that issue lies, be it at Google's end or outside of Google's network. That enables us to work with our partners and minimize the impact to end users, be it our end users or our cloud customers' end users. And as you can imagine, a lot of we serve about 1 billion plus users with this network, and they are dispersed geographically, so we're collecting all of these metrics from all corners of the internet. So what do we use these metrics for? First and foremost, we've built models to be able to detect and alert about fault conditions or near fault conditions. And then we take all this data to be able to provide a feedback loop and optimize our service delivery paths to our customers. And we also then take this data to be able to minimize the time we spend on troubleshooting and mitigating issues. And over a longer time, we collect these patterns and understand these patterns to be able to plan for the future and understand, to be able to plan out traffic growth and capacity as we go forward. So we talked about the metrics that we collect. We talked about how we use them. But let's talk a little bit about how we measure them, these metrics. Over the past few years, as platform density has increased to kind of go to include thousands of physical interfaces, and as the deployments themselves have changed, we have started to collect metrics that the number of metrics have actually grown exponentially, right? So traditional pull-based methods like SNMP and syslog don't really work much anymore. For example, a typical dynamically provisioned app could have been spun up, served its purpose, and been shut down well within a 5-minute time span that kind of is included in the SNMP polling cycle. So that makes our network operators run blind. So we needed a better solution. So what we did was we worked with industry leaders like Arista, Cisco, Juniper to be able to advance the state-of-the-art in device monitoring. We have been working to build and standardize streaming telemetry as a replacement for SNMP and syslog-like architectures. And streaming telemetry, what it does is it provides high-fidelity data, near real-time performance to be able to help us optimize for our traffic paths and provide more real-time performance metrics. We also work with ISPs worldwide to be able to provide them with near real-time performance measurements. Google maintains a global peering footprint with a generally open peering policy, and we provide access to the Google ISP portal to operators who share the direct network edge relationship with us. With this ISP portal, what our operators are able to do is they are able to get insights about how exactly Google's sending traffic and why that's the case to those specific partners, how we together can grow, and specific insights into actionable metrics actually into how to improve delivery quality and performance and things like that. So what you see here is actually a part of a snapshot of our Google ISP portal. And you can see that what we provide is basically ingress and egress traffic breakdowns, performance metrics like RTT, throughput, even video quality, and all the way go down to providing our partners with capabilities to be able to actually predict what their traffic growth looks like. So we also have ongoing investments on the product end, where we want to share more and more of these metrics with our cloud customers. I'll talk through a few of these products today. The first one of them is load balancer telemetry. So load balancer monitoring helps you get visibility into your internet-facing applications and perform diagnostics around that. It includes measurements like number of connections, latency for both the front end and the back end, and throughput. Let's talk about VPC flow logs. Think of VPC flow logs as equivalent to NetFlow for GCP environments. We are able to monitor everything that comes in and out of the compute. Right? It's near real time without any performance impact to you when you turn these on in your GCP environments. You can, again, measure things at the VPC network level or drill down all the way to the VM instance level. Firewall logs. So basically, firewall logs help you to get visibility into every connection attempt against a firewall rule that had logging enabled. So you'll be able to audit or perform forensics on all the connections that got denied or allowed over a longer period of time to figure out patterns. And you can consume all of this information in Stackdriver or export it to some of the third-party tools that you may have deployed today in your environments. We have integrations with some of the major partners, including Splunk, Sumo Logic, and many more. You can go check those out. So, in summary, you heard about our resilient network, you heard about the innovations and investments here and how we monitor it. Here are a few of the other networking sessions that you might be interested in that are relevant, that are going to take place over the next few days, and a link to our networking blog in case you're interested in following us for any of the future announcements in the space.